Greetings, everyone. This is our take on the application of the fractional Fourier transform to image reconstruction in MRI, which its authors are Vincent Patriot, Carlos Singlong, Carlos Lizima, Christian Tijos, Sergio Ubere, and Pablo Irarazabal. Without further ado, let's jump straight into the instructions. As the classic paradigm for the MRI requires a homogeneous B0 field in combination with linear encoding gradients, as distortions are produced when the B0 is not homogeneous. As such, several post-processing techniques have been developed to correct them. Therefore, we propose the use of fractional Fourier transform FRFT for analyzing and reconstructing the object's magnetizations under the presence of a quadratic field. The FRFT therefore provides a precise theoretical framework which opens a new paradigm for understanding the MR signal which is generated by an object under a quadratic field.
For theory part, we will explain the connection between the FRFT and the quadratic MR system. FRFT. This can be expressed as an integral transform as equation 1. The most notable difference between this equation and the FT is an extra quadratic phase in the kernel. U and rho denote dimensionless variables to maintain formal consistency. MRI signal under quadratic main field, the MR signal in a perfect uniform B0 field, ignoring T1 and T2 relaxations, and after demodulation at the Larmor frequency omega 0, it will get equation 3. Whenever there is an inhomogeneous field as a function of space, the magnetization is modulated by a time-dependent phase. It will become equation 4. There is a remarkable similarity between this expression and the FRFT defined in equation 1. Then, the link between the MR signal and the FRFT, represent equation 4 in the form of equation 1, will become equation 5. Both alpha and rho are function of time. Then, using equation 1, the signal equation becomes a time-varying order FRFT of the object as equation 6. These graphs are trajectories over a quadratic field in the polar representation of rho over space. For A, a constant gradient, B, a 2DFT bipolar gradient, and C, API trajectory. These three are examples of a one-dimensional 2DFT trajectory in the polar representation of rho over space. A. Standard Fourier interpretation. B. Fractional Fourier interpretation. And C. Variable order fractional Fourier interpretation.
Purpose of the experiment for this aim to investigate the process of decoding and image from the MR signal. Secondly, it seeks to validate effectiveness of field inhomogeneous equation algorithm. This study utilized a Philips 1.5 Tesla scanner with linear imaging disable for acquisition. Next, numerical phantom. By using a MATLAB to simulate the MR signal for 2D value, the design was based on reference phantom with same dimension, featuring 256 by 256 matrix, FOV of 25.6 by 25.6 cm, TE of 56 milliseconds, and a readout time of 28 milliseconds. Two similar signals were generated, one with uniform Inonn and another one with quadratic field. Reconstruction technique includes standard FT, invert FRT, invert VOFRT, and CP technique. Next, MRI phantom. The experiment using a fast field echo EPI sequence with acquisition parameter of 178 by 128 metric, FOB of 24 by 24 centimeters, thickness of 5 millimeter, angle of 20 degree, and TR by TE of 650 by 41 milliseconds. Data were acquired with 16 samples evaluated using a Q-body coil employing FRFT, VOFRT, and CP technique. Field map. From these three experiments, the matrix field was measured from these three images with different TE, which was determined along structural reference of the experiment. Next, image reconstruction. FT computation were performed by using a FFT taking less than 1 second, but FRFT and VOFRFT reconstruction were computed using EQ-A2. requiring 10 minutes for 256 matrix and 1.5 minutes for 128 by 128 matrix, equivalent to computing one-dimension inverse FRFT, for which CP reconstruction was computed using 2D extension of equation 10. So essentially the same computing time as VOFIFT reconstruction.
For the experiment result, let's start off with numerical phantom study. As you can see here on the left-hand side, we have 4 columns of image. The upper part represents the simulated reference images. The middle part are the geometric distortion of magnitude under quadratic field images. And the bottom part are representing as absolute images with respect to phase. Column A here is the inverse standard Fourier transform reconstruction. B is the inverse fractional Fourier transform reconstruction. C is the variable order inverse fractional Fourier transform reconstruction. And D is the conjugate phase reconstruction. In conclusion of the study, VOFIFT is the most diluted image caused by the low error in RMSE and MAE parameters due to the penalization effect, consequently making this method the best in reconstruction regarding to numerical phantom study. Another evidence is from the 3 graph below here, which showing us the VOFIFT method has the best trend out of all methods here. Next, we will go to Wirz study. This is the low distortion brain image of the volunteer, which used as the base image before going to reconstruction process. The figure A is the region of interest, B is measured field map, C fitted field map, and D is the comparison graph between measured and fitted field map approximated by a quadratic function. And here are the coefficients of quadratic function for the fitted field map. Next, we will go in details about the results. The CP method has the best value in image reconstruction of 2 parameters and also collect geometric distinction as well. However, this approach still shows both geometric and intensity artifacts, along with the noise especially occur in this method present in image D. Hence, FRFT with constant angle per echo and VOFIFT is outperform this method.
Discussion and conclusion. The MRI reconstruction is done by an inverse FT. This method rests on the base that the object has been magnetized with a perfectly uniform magnetic field and encoding using linear gradients. In a situation where these conditions do not hold and nonlinear fields come into account, second-order components are their first and simplest approximation. We present a new framework for quadratic field MRI analysis based on the FRFT. It establishes the theoretical relation between image space and quadratic magnetic field signals frequency space, allowing native second-order field image reconstruction, the FRFT transform, which is a generalization of the FT, has a quadratic phase term in its integral kernel, so that there is a natural link between the signal obtained from an object magnetized with a quadratic field and its FRFT. This new framework and the newly introduced low alpha space give a visual insight to the MR acquisition process and also provide a meaningful graphical representation that show the relations between the image domain, the standard K space, and FRFT domains. The FRFT reconstruction with a fixed order for the entire readout correct phase and a fixed order for each echo in a multiple echo trajectory correct geometric distortion as compared to the traditional FT. From a practical point of view, this is an important improvement when the reconstruction time is important because the FRFT can be computed with a fast algorithm. Additional work is needed to explore possible combinations of FRFT geometric correction with deformation techniques such as the grid warp algorithm, that would enable to map a geometrically distorted but otherwise artifact-free image from the FT reconstruction to the correct geometry of the FT reconstruction. Numerical experiments show that the VOFRT can effectively reconstruct MR signal under simulated quadratic field, correcting geometry and intensity distortions better than FG and CP reconstruction. Experiments in actual MR system show that under nearly quadratic field, our method is able to approximately reconstruct the image and correct some of its geometric distortion, improving over the FG reconstruction but not exceeding the CP correction, which take into account not only second-order component but also the exact measure field. The VOFRT method should not be prepared over the CP method for inhomogeneity correction unless the non-homogeneous field component is exactly a second-order function. One effect of analyzing the MR data using low alpha space is that it is scaled down by a factor CSC alpha n more than or equal to 1. This scaling is not homogeneous in k-space but depends on the time map of the sequence. For a given sequence span for ordinary k-space acquisition, this fact is now manifest as a resolution loss. This resolution loss could be reduced by using stronger gradients with an ordinary sequence or modifying the sequence to fill low alpha space at correct location. Additionally, new trajectories should be designed to fill low alpha space in order to meet image resolution requirements. Theoretical advances are also need to replace the Nyquist sampling rate for k-space with a similar criterion, which would indicate how information density is distributed along the low alpha space.